Hello, I welcome you all to this another interesting screencast. In this particular problem, we are going to draw the axial force diagram, shear force diagram, and bending moment diagram. This problem is coming from the engineering mechanics statics textbook, 13th edition by R.C. Hibbeler. If you remember, this problem is problem 717. And we did solve it, and I'll show you the final solutions for this particular problem. In the previous problem, we have been asked to find the internal forces at E. Internal forces at E for these two force members CB. The internal forces at E that we found were the axial normal force, the shear force, as well as the bending moment, right? So before finding those internal forces at E, we found the support reaction at A. We also found the internal force at this joint B, okay, as well as the reaction force at C. So we are going to use that information. We are not going to redo the whole process of redrawing the free body diagram. I'll show you a snapshot of the previous video that we did, and then we are just going to collect the support reactions quickly and replace them on this particular figure and then start drawing, because the whole objective of this video is to draw, right? So let's go to the page where we did this problem so that we look at the support reactions at A and C, and the internal forces at the joint B, as well as we need to find the internal forces at D, because we need to section this. So we need to section this beam here, okay, and section it there, all right, so that we have separate members. We are going to have separate members as shown here. If you've seen, we've separated all the members because we want the internal forces at joint, the reaction forces at the supports A and C, as well as the internal force at the member that we've sectioned at D. All right, is that fine? Great. So let's get back and have a look. So this was the problem that we did last time, right? So if you've seen, at A, we have 419.20, all right? At A, we have 419.20. Great. Okay, so let's replace these values. Like I said, we are not going to go through. If you want to understand how to find this support reaction, then you need to watch this video. All right, so let me just write down these supports. Okay, so we are saying at A we have a 1920 and a 400. Okay, and at B we have a 1920 in that direction, as well as 800. Okay, so this information is enough so that I don't get back again. At C we have 1920 at 800, right? So this information is enough. This one is for AB. Okay, AB, and then we'll transfer them later on. All right, so let's go to the next page. We've written down these values. So we are saying at A here we have we said at A we have 1920 in this direction. Let me use maybe red. We have a 1920. Okay, and then we have a 400, like so. And then also this side we expect to have the same 1920 for equilibrium. And then here at B we have 800, right, like so. Okay, and then at C we said we also have a 1920. Okay, and then we also have a 800. All right, so this information is fine, right? This is what we've done. So 1920 for 800, and then 1920 800, then 1920 400. Great. So this is fine. All right, okay, this is fine. So from this we are going to start from this end. So we are going to have here the equivalent force, which is just the length 6, like we said last time, by half. Okay, this one is half by 6 by 400. This gives us a 1200 newtons. Great. Okay. um it has chewed a lot of space on the other side. Let me start it from the back. So let me start it from there. Half by 6 by 400. This gives us 1200 newtons. Great. Okay, so now we are going to have a moment. We are going to have a moment that we want to find at this point. Let's find this moment at D and at D only. Okay, at D only we are going to have a moment. Let me replace these forces at B here. At B we are going to have we also have a 1920 like so, and then we'll have 800 like so, and then on the other end there we are going to have also a 1920, and then we'll have a no, this is 800, sorry, this is 800, this is 800, this is 800, sorry, and then this one is 1920. Sorry about that. And then this side we are also going to have a 1920, and then we'll have 800. But like we said, at D we are going to have a moment. At B we are not going to have any moment at B. All right. At D, that's a continuous member that we just sectioned. So 800 will tend to cause the beam to rotate like this. Therefore, our moment is going to be in the opposite direction like this. Okay. And the value of this moment is just equal to, again, you can apply the equations of equilibrium and solve there quickly. So we'll have 800 by the length, 800 by the length 6. Okay, so this gives us, what does it give us? 800 by 6, of course it gives us a 48, right? A 4800. So this one is a 4800. All right, and then here we are going to just have an opposite direction. Okay, we are going to have opposite direction of this moment. So this moment here is just going to be also equal to 4800, which you can confirm. 1920 tends to rotate. Let me write 1920 on the other end here. It tends to not be very clear because there are a lot of numbers. Let me put 800 here like this, and then I put this one as 1920 like so. So this 1920 will tend to rotate this beam like this. Therefore, we're going to have moment in the opposite direction, which is the reaction force. You can apply the equations of equilibrium, like I said. So this one you expect it also to be equal to 4800. Okay, because it's supposed to be opposite. You can confirm that by just multiplying 1920 by the length of BD. What's BD? BD is 2.5. You are supposed to find 4800. Okay, so 1920 by 2.5, you find exactly 4800 because you're supposed to have the same moment. All right, so I think we have all the information that we need, all the support reactions that we need. We have a two force member that we have sectioned at D and then included all the internal forces at D. The joint, we've separated it and included also the internal forces at the joint B, and then as well as at A, and so on. Like we said, we had solved this problem previously, so you just had to collect all the information from the previous problem, so that will reduce on time. So now let's start drawing. So we are going to be moving from the left, so positive will be up, negative down. Okay, and then for member BD, we're going to be moving from bottom to up. Positive will be on the left and the negative like so on the other side. Okay, here also positive on the top, and so this is how we are going to be moving. So let's start drawing now, and then we are going to use the same equations that we've been talking about. Okay, the rate of change of axial force, I'll call it just A prime, is equal to Q star, and this Q star, I want to differentiate it from the lateral force on the member. Q star, this is the axial distributed force, and therefore the axial force itself is just the area under the axial distributed force. And then V prime is also equal to the lateral distributed force, and therefore the magnitude of shear is just equal to the area under the lateral distributed force. And then M prime, this is when we say M prime, V prime, A prime. So A prime is dA over dx, V prime is dV over dx, and M prime is dM over dx. This is also going to be equal to shear V, and therefore the magnitude of our moment is just the area under the shear diagram. So these are the differential equations that we're going to use for doing the plots very, very quickly. Okay, at A, let's start with the axial force. We've seen that member AB is in tension, and that magnitude of 1920. So let's say this one goes up like so. Let's say this is our 1920. Maybe it's a little bit huge, so that we differentiate it with the other values, which are 1920. Let's say it's up to there, and then because we don't have any force, let me write down this value. This is 1920, okay, newtons. And because we don't have any axial force between A and B, no axial distributed force, we expect the slope of our axial diagram to just be the slope to be 0, and 0 is like this up to B. And then at B there the sign changes, okay, because initially we are choosing this sign that goes outwards as our positive. You've seen this value here, okay. So once the sign changes that at B, then that just simplifies closure, right? Closure, because they'll add up algebraically, right? So this is our positive axial normal force, which just means member AB is in tension. So this is A and this is B. Okay, great. And then this is D. We say this is D and this is C. So now let's go to D. We are starting from D to B, going up. Okay, so at D, what do we have? At D we have 800, and this in compression. 800 is in compression. We've seen the member is being compressed. So let's say 800 goes up to here. So we have this value of 800 here. Let's give it the number 800 newtons. Great. And then from there, we don't have any axial distributed force from D to B, axial like so. Okay, we don't have this. This is the axial distributed force I'm talking about. All right, so we don't have that, and therefore the slope of our axial diagram is just going to be equal to 0. So it will just be a straight line from D to B like so, and then when it reaches B, the sign changes there at B, which just see adds up algebraically, which simply means our beam has finally closed. Okay, great. And then let's move to C to D. Top is positive, bottom is negative. Let's look at there is undergoing compression, compression. and the magnitude of this particular value there is equal to 1920. So 1920 is down like so. Quickly, let's just plot that. Where are we? This, it will go down like this, and then from C to D we don't have any axis distributed force, therefore we expect the slope to be equal to 0, so it will just run like so. At D there the sign changes, which also just simply means adding up algebraically, which just closes our diagram like so, and this is equal to negative. All right, this is negative. Okay, let me wrap this so that I don't confuse us. Let me wrap this. All right, that is negative. So we have drawn this diagram, the axial force diagram. Let me put these magnitudes here. This is 1920 newtons, and this is 1920 newtons. Just like this one is 1920 newtons, but in tension, this one is 800. Great. So we've done this, we've drawn this. So we need to move on to draw the other one, which is the shear diagram. The shear diagram for member AB and AB. Let's start with AB. So this is our A, this is our B, this is our D, this is our C, and so is this A, B, C, D. Great. So let's go to our diagram for shear. Shear, what do we have? We have an initial value of 400. We have an initial value of 400 at A. So let's initialize point A there by 400, which is positive going up. Since positive is up, let's initialize this. There we go. We've done the initializing, and that value there is 400. That value there is 400 newtons. Great. And then from that value onwards, let's look at what is happening. We have a triangular distributed force. Then we know from these equations. Let's look at AB. Okay, AB. So Q is what is Q? Q is negative, and it is increasing. Okay, therefore you expect V prime to also be negative and increasing. And what is this magnitude? Of course, we can work out the area under that, which is just equal to half times the intensity minus 400, therefore the highest, and then or the largest at the top, since that's a triangle, then by 6. So this gives us a minus 1200. So therefore the 400 will subtract from 1000 so that we find the destination. We find here we are looking at our VB. Okay, moment at VB is, shear at VB is equal to 400 minus 1200, which just gives us a minus 800, right? A minus 800. Okay, so that is our final destination. But when we look at our slope for our shear, we said is negative also and increasing. All right, and our load is being governed by a polynomial of degree 1. That's a linear function, polynomial of degree 1. Therefore our shear will be governed by a polynomial over degree 2, which is going to be a quadratic, right? A quadratic function. Great. The slope is negative and increasing. Therefore I will not show you two slopes to choose from. I've done that in the previous video. Just go directly. So the slope that is negative and increasing, it will start from there. It will be something like this. Okay, let me draw it properly. I want to arrive at two squares. All right, something like that. Is that fine? Great. Something like that. It may not be perfect, and it will never be. So this point here is 800 newtons. This point, this one here. Okay, that's 800. Let me just remove that. Send that, and then when we reach B, we have 800 for closure. You've seen this 800 down here. This one here, you've seen this one. So this one is positive, and then we have a negative, so it is minus 800 plus 800, which gives us a 0. So a closure is supposed to be there, right? So business has to be closed so that we get our profits. Do we? Or increase our investment? I don't know. All right, okay. So there we go. This is quadratic in nature. Okay. Let's now draw from C to D. From C to D, why do we have C to D? C to D, the initial value at C. What's the initial value at C? The initial value at C, let me move this C of mine. I move it somewhere so that it does not disturb me. So let me put it down here. So positive is up at C, that's our initial value. So it's going to go up like that. Okay, that's 800. We've seen this one here. We are looking at C. C, we have an initial value there of 800. We have initialized, okay, our shear diagram. This is 800 positive. And then later on, this is going to move going this side. How will it move? Of course, it will go like so. Let it go. Oh no, Lord, have mercy. There, like so. Okay, and okay, I need to move this. Where will I put it? Okay, I'll put it somewhere else. Can I put it inside here? 800 newtons, and then I put an arrow to say this one here. Okay, I think it's visible. I hope so. All right, so 800 there we are saying we don't have any lateral distributed force from C to D. Therefore, we expect a constant slope for our shear from C to D, and it will just be a straight line like so. We just run there up to there, and then when we reach D, our value of our shear becomes negative. Therefore, the two are going to add up algebraically, and when that happens, then it's going to be closure. Here, I think I need to use a different color. Let me use blue so that they are different. Let me use blue. Sorry, like so, and then we say it like so, and then there is going to be a closure. It's going to be a closure like so. Great. And what do we have? That one is positive. This is positive. I'd forgotten to indicate, and this is negative. Great. All right, so we have a shear positive up there from C to D. Now let's go to D to B. We are starting from D going to B, from D going to B. So let's look at the initial values. What do we have? So at D, we have the initial value of 1920. Okay, let me do this. My space is running out. Let me move this down like so. Oh no, Lord have mercy. Okay, the space is running out. These things, I think they need to come here. They need to come somewhere here because they are chewing all my space. So let me just create a boundary. I will delete it later on after we do this. Okay. All right, something like this. All right, there we go. So from D to B, what do we have? We have a 1920. Where is our D? Let me just show you where it is. Let me just show you. Our D is here. You've seen this? We have a 1920, this one here. You've seen this one? That's our initial value. Let's initialize that point, okay? And it's going towards the negative, like so. Let's say our 1920 goes up to there like this, okay? Okay, we can, okay, up to there is fine. All right, that's our 1920, okay? Let's give it a value. This is, we say this 1920, this is 1920 newtons. All right, and then later on, we don't have any lateral distributed force from D to B. Therefore, the slope will just be 0, the slope will be 0 from there to there. And then when we reach B, then we have a closure. We're going to have a closure. We are going to have a closure, right? We have a closure. Okay, so something like that. We have a closure, and then we have 1920 newtons. Great. And that value there is negative. Okay, it's negative. Okay, remember we had said positive on the left, negative on the. Okay. Moving from D2. So in fact, this one, let me use another color. Sorry about that. Let me use another color. I use red so that for this one I'm supposed to use another color, so that because we have 3 members, that I use red. So there we said this 1920, the shear, and then from there onwards we have this from there to there, and then like so. Great. And also there, let me mimic the same like so that each member has a distinct color. It is easier to follow. Okay, great. And then our blue starts there like so. We make it uniform. Each member has a different color. Great. It's just easier to follow because they are different members, so that where they interact and so on, it's easier for us to follow. Okay, let's go now to the bending moment diagram. This is the one that is a bit interesting. So what is the initial value at A? No initial value, no moment there, so moment starts from 0. Great. But when we look at our slope, let's redraw this. When we look at our slope, what's our slope? V shear is positive. Where are we? We are from A to B. Our shear V is positive and is decreasing, right? Therefore, M prime will also be positive and decreasing, right? Great. And the magnitude is the area under the shear diagram. So this we cannot just work it out exactly. One, for us to find that magnitude, we need this distance there, right? We need this distance from here, where we have shear becoming equal to 0. Okay, this point here. We need that point. Okay. We need that point here where shear is equal to 0. We need it. So how do we find this? Again, it would be up to you. There are a number of techniques. You would section this if you want to. You'd section this. You have A there. What is A? You have a 400. You have a 400 by 420. I mean by 1920. And then you'd section this at just an arbitrary distance along X. You know this sectioning where you have V, you have M, and then you have the normal force. Okay, then you should know this Q, which is the function governing this load. So Q is just an equation where we're writing this in terms of gradient and some intercept, and we know our gradient is positive there, which is just a change in y divided by the change in x, and our x is 6. So this is our gradient, and then 400 divided by 6, that becomes our gradient. So our m is just equal to 66.6667. all right, so that would be, so therefore this we can write it as, if you want to maintain it, just 400 over 6, okay, by x. The intercept is equal to 0 because we are starting, A is assumed to be our origin. So this is the equation. So this is one way you can do that. Okay, so you'll have a function like this, and then you need to find an equivalent force. An equivalent force which is just half times x times q. Okay, times q. Okay, and then when you multiply this, then this gives you This gives you 200 divided by 6, then x squared, right? Something like that. Yes, because x will cancel there, 200, and x squared, like so. Yeah, so you're going to have that as your distributed your equivalent force, which is going to be acting at the distance. It's going to be acting at the distance. What distance is this? This distance here. This distance is 1/3 of x. Okay, so you can have this. Okay, this is one of the methods. All right, I think this is much faster. Or if you want to, you can use this same differential equations. We know v is just integral of q dx. Okay, and then later on you'd go on to integrate this. So which one do you want us to use? Okay, let's use the v is equal to q dx. So this is one of the methods. All right, you'd find q, or we're going to use this other technique. So we want to find q at this point. So let's find a general function for this, because the function is being governed by a continuous function from a to b. All right, so we'll say v, okay, just vx, okay, to a known distance, or just v as a function of x. V as a function of x is equal to the initial value at a. Okay, so we are talking of from a to so let me write here. So from a to b, so we are going to say v from as a function of x is just going to be equal to the initial value at a, which is 400. Okay, that's 400. Then minus, because we need to subtract. The following shear is we are subtracting by the area under the shear diagram, and that is negative. All right, so minus the integral of q, which is the lateral distributed force, dx. Okay, and then our q, we already said this q here, we said this q, writing it as a function like so, we said it becomes equal to 400 divided by 6, 400, which is gradient change in y divided by changing the x, then x. So this is our q. So your q, we said is just 400 divided by 6x. Okay, that's our q, because when x is equal to 6, q becomes maximum of 400. Then vx, therefore, now is just going to be equal to 400 minus the integral of 400 divided by 6x dx. So finalizing this function, our vx as a function of x is just 400 minus, when we integrate that, what does it become? It just becomes the 400 divided by 6. We'll leave it as an indefinite integral. Okay, and then this just becomes x squared divided by 2. Okay, just like that. Okay, and then finally our vx just becomes equal to 400 minus 200 divided by 6x squared. All right, so this is a general equation for our vx. All right, are we there? This is a general equation which you could have also found if you just section this member. It's up to you which one you use. Right, you can get to whichever is faster for you. I chose this one, and then you can use the other one for section. You'll find the same equation. All right, this equation that is governing our shear from a to b. And once we have this section, then we know that our moment, all right, our moment is just the area under this function, right? So now let's find the moment. Okay, moment as a function of x is just equal to integral of v dx, okay, which is just equal to integral or 400 minus, or we can start with this writing it properly, 200 divided by 6x squared plus 400 dx. Okay, and then if we were to integrate this, then we're going to have minus 200 divided by 6x cubed over 3. Okay, these of course we bracket them, then plus 400x. Again, we are not going to include a constant. We'll leave it just the way it is, as now a general equation for our function from A to B, which is the area under the shear diagram. But we want to find x. So so we have a function now for moment, we have a function for shear. So how do we find x? For us to find this x, we just make v of x equal to 0, right? So we use this equation. Let's find the x. We use this equation, and once we find the x, then we can plug it in the equation for our moment, so that we find that particular value, right? Great. Okay, so we are using this equation now, this equation which is quadratic. We're using this equation so that we find the value of x. So we know that x, when x is equal to 0, our shear is going to be equal to, when v is equal to 0 at this point, then we are going to find the value of x. This is what I meant. So now we'll make v of x equal to 0, okay, which gives us an equation 200 divided by x squared plus 400 equal to 0. So this is a quadratic, okay, which we can solve. Let's solve it. So this becomes just a 200 divided by 6x squared divided equal to 400. And then let's find what x is. We're going to find two values. So what is this value? So we have 400 divided by 200 divided by 6. So we have one value. We have x squared equal to 12. All right, and therefore our x is just going to be equal to root of 12. This is plus or minus, right? So it will be plus or minus, right? Root of 12, which just gives us a 3.464. Right, so that is fine. That is really fine. Let me just check my work again so that I avoid any small errors. Okay, great. So that is the value. So this x here, this value of x here, of course, will not get negative. Negative doesn't make sense. We get a value that makes sense. It's a positive. We are starting from A. So this is 3.464. Great. So once we have that value, sorry, my calculator was almost falling. Once we have that value, then we are going to use this function, seeing this function that we found for moment, to just find the moment at this point where shear is equal to 0. At this point, our shear is equal to 0, and that's where we are going to have maximum moment. So we have the function for our moment, we just plug it in. So just say moment at 3.464, right? 464 is equal to, what is the function? The function is just down there. So it's a minus 200 times x cubed, and then we just put our 3.464 cubed divided by 6 by 3, which is just 18, then plus 400 by 3.464, then we close, and then we'll find that our moment will be equal to, what is our moment? Okay, our moment is going to be equal to 3 point, let's find our moment. Our moment will be equal to minus 200 times 3.464 cubed. divided by 18, divided by 18. Well, this 18, sorry. When we integrated this was, okay, it's fine, right? It's fine. So divided by our 18, and then what do we have? 18 then plus 400 times 3.464. What do we have? We have a bending moment of 923.76. Okay, let's repeat it. Minus 200 times minus 200 divided by 18 times 3.464 cubed plus 400 by 3.464, 923.76. Okay, so that's a value we find there. So let's do the plotting. So what is the slope again? Slope is positive and decreasing. Sorry for taking most of your time. So let's do the plotting. So from here, from point A, we expect a slope that is positive and decreasing. So we are going to rise like this up to that point. So this is a polynomial of degree 3. We're able to see it, and that point we are saying is equal to 923.76 Newton meters. Great. So when we reach that point, we need to go to B. Of course, we know it's going to close. We need to go to B. It's going to close. That other value will have to close. Okay. So from the maximum point, let's find the moment. It's supposed to give us a 0, this equation. If it doesn't give us a 0, then there's something wrong, right? So instead of now, let's find the final value at the end. Let's plug in the final value of x, which is just a 6, and it's supposed to give us a 0. So then m of x at 6 is equal to minus 200 divided by 18, and then we have a 6 to the power 3 plus 400 by 6. Okay, the whole length. Okay, so minus 200 divided by 18 times 6 cubed plus 400 by 6. Great, so it gives us exactly a 0. Great, so this is closing. Great, it's closing. So this is going to close. Oh, come on. Was I afraid of a B? Yes, I was afraid of a B, hence my curve became disturbed. Great. Let me write this somewhere inside like so. Great, and then I'm going to just go okay, it has closed. So this is our plus. Great, this is our plus. So we plotted this function for moment, which is a polynomial of degree 3, and you saw all these steps. This is what took a little bit of our time. Okay, it was the issue of finding where we have the maximum, and we know that point is 3.464. This is where we have the maximum moment. Let me just get rid of all this stuff. Great, and then the rest is just direct. The rest is just direct because the equations are much easier to work with. All right, let's do the plot for CD. Let's do the plot for CD. Okay, let's do the plot for CD. For CD, what we have shear. CD shear is positive and is constant, and then we expect the slope of our moment to also be positive and constant, right? And the magnitude of this moment is just equal to the area under the shear diagram, which is 800 by 6, which just gives us a 4800. Okay, so let's do the plot for that. So let's write down C there somewhere there. So it's constant, and positive. So 4,800, let's say it goes up to there like that. Then when we reach D, and we are using another color here, we shouldn't forget, okay, like so. Then when we reach that point at D, we do have a moment which is in a counterclockwise, and if we are to take a section, we are going to have a clockwise, that we are using the opposite sign of what we have at our section. So the opposite sign of this moment here is a -1, which is going to add up algebraically with our value that we just found. So we'll have 4,800 and minus 4,800, which gives us a 0 and hence a closure. So this is how this is going to close. Okay, this is going to close like so. It closes there, and that value we said is this value here. This value here is, let me indicate the sign here for this. The sign for this is negative, right? Negative. Okay, so we are saying this value here is equal to 4,800 Newton meters. Okay, and is positive. Great. Then let's now do a plot from quickly from D to B. From D to B. Okay, what do we have? From D to B. From D to B, we have shear, which is negative and constant. Therefore, our M prime will be negative and constant, and and then M itself, the moment, is just area under the shear diagram, which is just going to be equal to 1920 minus 1920 times the length, which is what's the length of this, which is just a 2.5, and this gives us a minus 4,800, right? By 2.5. Okay, and the slope we said is negative. We are moving from D to B. Okay, negative slope is in this direction like this. Let me move this. I put it inside 4,800 newtons. All right, so now negative slope from D to B will be like this. It's like this. We are using red, so it's negative and constant. So we are going to move like so. So our slope, so our initial value at this point at D is, we do have an initial value. Our initial value is, if you've seen the direction that is here, look at this direction here. We have a clockwise, which is negative, but we get the opposite, right? Because the internal moment will be opposite to counter that internal moment. Therefore, we are getting a counterclockwise, which is positive. All right. So we'll have an initial value in the positive. Since this side is positive, this side is negative. So we are going to go in like this. We'll go in like this. Let's say this is our value of 4,800 up to somewhere there. Let's say up to somewhere there. And once we reach that value there, let's indicate it. This value here is a 4,800 Newton meters, and then we are saying the slope is negative and constant. So move from here, move from there to B, where we don't have a moment at B. Okay, because B does not transfer any moment. Okay, so something like that. Okay, something like that, and that moment there is positive. That moment is positive. Okay. Great. I think this is about it. This is really about it, and I hope the video was helpful. I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing, and liking my channel. Let me just get rid of this so that my slate is clean. I just get rid of all this stuff. All right, there we go, and we are done. Bye bye, and see you in my next screencast. Give me a thumbs up, like my video, and continue subscribing.